Hi everybody, welcome to another video that will help you guys calculate generation time. So this is going to be after you guys have collected your data in lab, and now we're going to graph it, and then from that graph do the calculation. So again, just as a little bit of a disclaimer, this is just sample data, so please make sure you're using your data that you got from class. This is just to show you how this is calculated. So just a little bit of a refresher on generation time. It is the time required for a population of cells to divide during the log phase, and that is super duper important, so I'm going to circle it, of the bacterial growth curve. So this is actually the equation that we're going to use. It's just a little misleading because it looks super duper easy. It looks like you're just going to divide two different numbers together and get the answer, but there's actually more of a backwards a backwards method in calculating this generation time using this equation. So before we move on though, I just wanted to also give you guys a refresher on what log phase is. So just a little bit of a refresher as to what a growth curve looks like. Let me just draw kind of a wonky looking graph here, but this is your bacteria growth curve. So ideally, our growth curve should look something like that, right? So if you're just here for the calculations, you can totally skip this part, but I just want to make you guys aware that in our lab, the graph that we usually get is just going to be this part, right? And that is the shape that we're looking for. So again, excuse me, just to review, right? This is our lag phase, this one right here. This one is our log phase, our stationary, and our death phase. So just like the definition said, we are looking for the log phase to calculate generation time, right? So we're looking for this increase, that yellow one that I just highlighted for you. So here's the standard curve for E. coli. We're going to visit that again later. So here's our pretend graph. Right? And again, we're going to be using the equation from the previous page, which is this one. So I'm just going to write it out. 2 times 10 to the negative 8 x. And I do put the parentheses on there just so I don't forget any of the numbers, right? So after you guys collect your data, obviously the first thing you got to do is you have to graph it, right? So this is a sample graph of how that would look like. Yours might look different, but the shape should be about the same. It should show you if we're reviewing here, lag phase, this should be log. And if we continue it, this would be stationary, and then this would be death, right? So now that we are acquainted with our graph, now we're going to actually solve for stuff, right? So let me zoom in. If you are on Excel, if you hover over these data points, it'll actually give you the number. If you're given one of these for like a quiz or an exam, then just estimate to the best of your abilities. Usually your lab instructors will give you guys some kind of leeway in terms of acceptable answers. So when you're picking a part of the graph, you're wanting to pick a part of the graph where the log phase starts, but not at 0. So for example, like this one right here, right? You might be tempted to start with that one. The problem with that one is if we write out the coordinates, it's 1, 0, right? That's going to mess up our calculations later. So you want to pick one that is at the beginning of the log phase that doesn't give you a 0. So I would actually pick this one right here, right? I'm going to estimate that one to be, let's see, so that's about like 1.5 and 0.1, something like that, right? And again, if you're in Excel, you can more accurately tell what those values are. And you have to find the top of the log phase before it turns into stationary. So ideally, it could be one of these, right? As if I was your lab instructor, I could probably do either. So I'm just going to do this one though, because it's a nicer number. It's right there. So I would read this to be 5, let's see, 1.5, something like that. right? So then if we were to put steps into our calculation here, the first thing that we need to do is we need to plug in absorbance values, which is what you collected data from, right, for y. So that means I'm taking this number and this number, those are the y coordinates, those are the absorbance values, right? I'm gonna plug them in into this equation and then be able to get b of I and b of f. If you don't know what b of f and b of I mean, then go back to your PowerPoint. Everything will be there for you. I'm just assuming that you already know what those variables mean. But if you don't know what those variables mean, then go back and take a look at them. So let us calculate here. So we're going to start with the bottom here. So this is our initial time. This is our final time. That's what b of I and b of f is. It's b initial and b final, right? So what I'm going to do is I'm going to take that equation, y equals 2 times 10 to the negative 8 x, right? And don't freak out, there's no y-intercept, right? There's a 0 right there. You're welcome to keep it there if you want, if it makes you feel better, but you don't need it because this is 0. So I'm going to plug in 0.1 for y. And I'm just rewriting this so you can see my work. And then essentially you're dividing both sides by that exponent. Right? If you're doing this in the calculator, please be very, very careful about the exponent. So give me a sec. Let me plug it into mine. So 0.1 divided by 2 times 10 to the negative 8 gives me x equals, let me count my zeros, 1, 2, 3, 4, 5, 6. So that's 1, 2, 3, 4, 5, 6. Right? So this would be aka our b of I. Right? So then let's do it for the second one. Same equation. Don't know why I put a you can do either one. You don't need to put a parentheses on the x. Right? So then up here it's 1.5. Whoops. 1.5. Right, so I plug that in for y, do the same thing, which essentially means that I'm dividing both sides by 2 times 10 to the negative 8. Right, those cancel. So then I would get x equals, let me just plug it in, 1.5 divided by 2 times 10 to the negative 8. And got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right? So this is b of f because those were the equations, or sorry, the variables we're looking for, right? So what this means really is this is the number of cells, right, at beginning of log phase, right? And then I'm running out of space here, but this is the number of cells at the beginning, or sorry, not at the beginning, at the end of log phase. So we're going to use those numbers for our next part, right? So it's going to be this number and this number right there. So I'm going to need a fresh page, so I'm going to scooch to the next one. Okay, so then we're going to solve for n. So that's our next step. I think we're on step 2. So solve for n. Right? Remember at the equation at the beginning, it was g equals t over n, but we need to solve for n first before we get there. So we don't need this yet, so I'm just going to erase it. So what we're going to do is we're going to use the equation that was given to you by your lab instructor. So that's n equals 3.3 log of b of f over b of I, just like that. And then you're going to take the values from the other side and plug them in. So I'm going to use 3.3 log. So my b of f was the 75. Let's see. I have 6 zeros. 1, 2, 3, 4, 5, 6. And then the other one was 1, 2, 3, 4, 5, 6. Also 6 zeros. So 5, 1, 2, 3, 4, 5, 6. right? If I were you, I would take this one a little bit at a time. So let me calculate it. 3, 4, 5, 6. And divided by 1, 2, 3, 4, 5, 6 zeros. Log of the answer times 3.3. So then I get n equals 3.88. So we'll use that for later, right? Excuse me. Then the last part is going to be to actually solve for generation time. So now we can use the beginning equation that I talked about, which is why I said that this is kind of a backwards way to get there, because the equation is so easy, but takes us a little bit of time to get there. So t is time. So then I'm going to refer back to my graph here. My time is going to be the 5. Let me change colors here. So that's my final, and that's my initial. So I have to subtract both of those. So 5 minus 1.5. So let me go back over here. It's 5 minus 1.5. And then my n, we already calculated, which is, 3.88. Right? So let me just math that really quick. So that's 3.5 divided by 3.88 divided by 3.88 gives me 0.9. And then you can put, however many decimal places your lab instructor asks of you. I'm just going to keep it there for now. So it's 0.9. And for this case, it depends on what you're looking at, right? Because this one, our axes, and this case is hours, right? So if it's minutes, make sure you put minutes. If it's seconds or hours or days or whatever, make sure you have the proper label. But in this case, this one is hours, right? So that means that growth from the beginning of log phase to the end of log phase, it took them 0.9 hours to do that. So not even a whole hour, right? It's a little bit under an hour for it to increase that much during log phase. And I'm sure you guys know this, but I'm just going to mention it anyway. There are a lot of factors that can determine the increase or decrease of the rate of growth of your bacteria cells. So that's something you can ask your lab instructor about if you do have a question. But I hope that makes sense. Again, just as a reminder, this is sample data. So you gotta make sure to graph your own data first. You can follow the same steps of the calculations, but the data will be slightly different. If you have any questions, make sure that you reach out to your lab instructor, and I'll catch you guys in the next video.